Okay, great. Um, so now if you look at this, right, digital things, so you have a flop, you have a flip flop, and then you have a circuit, combo circuits, correct? Combinational logic. Okay, now the same way it is, we look at flip flop, combinational logic, and then flip flop. Now, if I'll show you in the design, you see this, the whole thing that you see, this is your flip flop SDFF, and this is your flip flop SDFF. But between them, these are all the kind of logics. Say there is a buffer, inverter, OR gate, NAND, AOI, and then you have full adder, and three input and then you see here mux. Okay, and you have your again full adder here and full adder and again and so these are all something that we call it as cells, and this is something that we call it a net. What is the meaning of net? So it's basically connecting your output pin to the next input pin, that is called net. Okay, so the whole thing till your flop. So we just write the whole thing. It can be any logic. So it would be tough for you to write, okay, this is the logic. So what we usually do is in the industry, we always just write it like kind of or draw it like kind of say register, a combo logic, and then a register. So this is how we write it. Okay. So this is reg to reg. Okay, this combo logic can be anything. So here you may have it different cells, but in the another path you may have again multiple paths. No, there could be a different cell. So we always just say this way. Okay, and this is your say this particular one path. Okay, and the corresponding things is going to be say something like this. This is the place where it is kind of the starting, where it is starting. Okay, so this is the flip flop. The logic goes through AND gates and OR gates and different things. They are all sitting nearby, and then finally it will ends here. Okay, so it's called path traversing. So you just traveling along the path, how the path is going, traveling. So these are all some things that you would learn and really going to be interesting. Okay, all right. Leaving this aside, moving on to the actual topic that we wanted to. Okay, so CMOS circuit designs and okay, the layout part. Okay, so in this chapter we are going to talk about, or we are going to learn basic MOSFETs. Okay, how a MOSFET operates and what are the different types of MOSFETs, and which is the one we use in industry. And we also try to design our circuits, the schematic for the gates, and how that would be implemented in the IC. That is something that we call it as the layout part. Okay, so uh, that is what going to be the agenda for this particular module. Okay, moving on. So MOSFET. So we everyone would have gone through about there is so the first element that semiconductor you would have come to learned is PN diode or PN junction diode, right? And then you would have learned BJT, and then you would have learned MOSFET. Okay, and probably in the latest stages we have different families, but this is how you would have spent time or probably learned in your college days. Okay, now which is the one we use currently? So remember, we don't use BJT and all anymore. We are talking in terms of lower nodes, 7 nanometer, 5 nanometer, and 3 nanometer, and we don't use BJTs and all anymore. Okay, so then what is the advantage of MOSFET? So advantage of MOSFET is something that you can scaling down. Okay, Now, what is the meaning of scaling down? So the meaning of scaling down is basically, give me a minute, let me just pull up. I'm just opening the PPTs just a second. So what is the meaning of scaling? So the scaling meaning, you have your the transistor, and this transistors can be scaled down. Okay. Now if you look at this, say this is your the transistor size in say 90 nanometer. Now the whole transistors can be shrinked. The whole transistor can be shrinked, including your gates, the whole structure. Okay, so this shrinking is something that we call it scaling. Okay, this shrinking is what something that we call it scaling. So the MOSFET have offered, probably it has offered a great future in terms of scaling. So that is the main reason for us to you know keep going down and try to scale as much as that you can, or different technology nodes and etc. Okay, so it is something like, see, you have a bigger transistor now, try to bring it, say, kind of smaller one, and say this going fine and this going fine. Now the next set of research that keeps going on for little smaller size, and so your overall transistor size is has really reduced a lot. Okay, so this is something that we call it a scaling. Okay, so MOSFET offers the great scaling, okay, feature. So that is the main reason we always rely on MOSFETs. Okay, now moving on. So MOSFET is basically metal oxide semiconductor. So metal oxide semiconductor. Now what is this meaning? So this meaning is, this p-type body is nothing but your semiconductor. Okay, this p-type body is nothing but your semiconductor, and you have your this oxide. Okay, and then on top of this is the gate is kind of a metal. So now this is the structure. It's basically kind of the sandwich structure. I'm sure everyone knows what is the meaning of sandwich. So this is something that we call it as a kind of the sandwich structure. Okay, now the name says clearly metal oxide semiconductor. Now, so any MOSFET that you take, there would be there would be four different pins. Okay, so it's basically source, drain, gate, and bulk. Okay, so they would be always there would be always four pins. Now, what is this MOSFET? Remember the conductivity of the path between two contacts. The source and the drain is altered by the voltage applied at the gate. Now remember, source is something that kind of energy source, or say source, energy source. Okay, energy, where the energy is available. Now you try to turn on the gate. Now the drain gets charged. Okay, the drain gets charged. Now when I say drain gets charged, what does this mean? When your gate is on, so it's basically your more than threshold voltage. So we will talk about what is threshold in a while. So when your supply voltage at the gate goes beyond the threshold, the gate kind of open, or probably on, and the drain starts charging. So that is the behavior of a MOS. Okay, so it is basically you are transferring the charges from source to drain when the gate is on. That's a simple word. Okay, so any question here? Just a basic MOSFET. Okay, and remember, as I mentioned, there would be always, there are going to be four different, pins now, but we draw only three always. So we will not, draw a bulk whenever we are drawing any kind of schematic in our regular day-to-day basis. Okay, so that means, so you have something like gate. See this something like source and then drain, and the bulk is going to be somewhere over here. The bulk is going to be somewhere over here. Okay, remember, this bulk is always kind of assumed to be at ground potential. Okay, so the bulk is going to be assumed at a ground potential if it is a NMOS, and it is going to be treated as 1 if it is a PMOS. Okay, so your gate is going to be a different pin, individual pin, and source is going to be another, pin, and then drain is going to be another pin. Now your bulb, something that we would, if it is a NMOS, then the bulk would be assumed to be at ground potential, and if it is a kind of PMOS, then we call this as a well, N well. So N well. So I'll explain you everything. N well. Okay. So it is assumed to be at 1, basically at VDD. Okay, now moving on to the next one. Look at this. So this is your silicon substrate. Okay, now what is it you are doing here? You are actually, first thing is you are adding impurities, converting it into N type. Okay, now N type, so this is also converted as a N type area. Okay, now this can be treated as a source and this can be treated as a drain. Now, the distance between these two is what we call it as a kind of the length. Okay, this is something that we call poly length. Okay, now this distance is, as I said, length. That is basically nothing but we call it as a technology. Okay, so when I say technology, that means, say if I'm saying 90 nanometer. Okay, so it is going to be 0.09 micron distance between these two, because these two distance, no, this is going to be 0.09 micron. Okay, so what is this meaning of micron? That is a basic uh, unit that we measure it here. Say for example, now if I have to measure this, say you have an area, no, say for example, now I have to just measure. So now this is, the distance is 0.608. Okay, you see this distance is 0.608, but the length in case, right, it would be 0.09. So that means inside the cells. Okay, so the technology is basically you go and design the cells based on the technology. Okay, now since we are learning the basics of MOSFET, let's keep technology aside. Let's try to understand a basic MOS. Okay, now this is becoming a source, and this you can treat it as a drain, and this is your, the oxide, the silicon dioxide. Okay, or people call it, polysilicon, and this is kind of, say the gate. So people, call it, say, kind of, metal, and these days a different hafnium. So different materials. So this, say, end of the day, you just need to understand this as a gate. Okay. So this is how your cross sectional view, this is how it would look like in your what do you say, the silicon. Okay, the cross sectional view. Okay, now this is kind of, the basic MOS schematic, and this is how it would be in the what do you call, the silicon. Okay, now let's go and try to understand the different types of MOSFETs. Okay, and so you turn on the gate. Okay, you supply a voltage at the gate, and the charges would travel from here to here. That's it. So basically, drain gets charged. Okay, and remember, MOSFET is a voltage controlled device. Voltage controlled device. Simple, nothing else. So it's something. BJT is known as current controlled device. Okay, whereas MOSFET is something that we call it as a voltage controlled device. Okay, and the next thing is different types of MOSFET. So we have two types of MOSFETs. So one is basically enhancement MOS, and there is a depletion MOSFET. When I say enhancement MOS, so by default it is off. Okay, if you wanted to turn on, then you need to supply a voltage at the gate. Okay, that is what called enhancement MOSFET. Now, when you say, or when I say depletion, this is by default on. This by default on, and you have to just supply a voltage to make it off. Okay, that is a basic thing. So you need to just supply a voltage to make this off. So that is a difference. Now, which one we would use? So what is it you're using in home? Are you using its kind of, switch? All, how is your electricity that you're controlling? You have a switch and you turn it on. Say here it is your, uh, electricity tower, right? And you have a switch, or the meter box, and then you have your bulb here. Okay, now, so you turn on the switch and you control the light. So the same way the enhancement mode MOS operates. Now if you look at, this is what we use in industry, this we don't use at all. So I have never seen any kind of depletion MOSFET that is being used. Yeah, it is available, but we don't prefer using this, because remember, in industry we always worry about power also. So if you guys have gone through the previous classes, right? So there is something that always I talk about, PPE, power performance area. So we always need to worry about power, performance, and area. Okay, so we will not have any kind of transistor that is on by default, and we try to use the ones which are kind of, the one which is by default off. Whenever you want it, you may turn it on. That is how it is. So enhancement type MOS is what we always use in our industry. And moving on to the next one. So there are two types of MOS. So one is NMOS and another one is PMOS. Okay. So what is this difference here? So NMOS would be kind of, say, the electrons are going to be majority. Okay. And the holes are going to be minority carriers, right? So for the NMOS. Okay. But in case of PMOS, we have a holes as majority. Okay. And you have electrons as a minority. Okay, so that is the main difference. Now, so which is going to be faster? Is NMOS is faster or PMOS is faster? Because NMOS is going to be faster because electrons are always faster than the holes. Okay, so remember, these are all a basic interview question you should be knowing. Okay, so NMOS is going to be the one which is always faster than PMOS. Okay, so uh, we always kind of look at both PMOS and an NMOS. That is what we call it, kind of the CMOS. So what is the meaning of the CMOS? Meaning it is a complementary MOS. Complementary MOS. Okay, it is kind of both PMOS plus NMOS. Okay, so both PMOS and an NMOS. Okay, together, if you can add it in your design and style, then it is, we call it a kind of the CMOS. Okay, now let's try to understand how an NMOS operates. Okay, so before that, remember, there is some important property that we always use when it comes to MOSFETs. That is something that we call it WL. Okay, so this is something that we call it. Say, look at this from a 3D structure. Say this is your kind of front view. This is what you have it here, right? Now look at this from a 3D structure where this is your front view and this is kind of your side view. Okay. Now remember what we discussed. We discussed about this is treated as a L. It's called poly length, or probably people also call it gate length. Gate length and the width. Basically, this is the, say, if you try to understand a bridge constructed on the road. Okay, say for example, this is a kind of drainage which is passing the water from here to that other side of the road. Now the this is something that your size of the canal. Okay, and this is something on the road. Now look at that from that angle. Now say wider the road, more vehicles can travel. Now imagine if the road is kind of smaller, only less vehicles can travel. Correct. Now when I say that, that means your W is something that has a major role in your overall delay of a transistor. Now we'll talk about that in a while, but I want you to first understand what is the meaning of length and what is the meaning of the width. So any question here? Is it clear, or anyone has any questions? I can just quickly answer your questions, if any. Hmm. What is it going to be reduced? Nothing like that. No, because you reduce your W. I mean, basically you reduce your L. So that means, though you reduce your the whole device, but since you are reducing this L, so you will not be losing out anything on the efficiency. Okay, yeah. So we'll talk about that. It's too early for us to talk about. Let's understand the basic MOSFETs and operations. Then we will go on learn the MOSFETs, the scaling and etc. The advanced nodes and etc. Okay. Now assume what is going to happen if you reduce this L. Say simple, right? Now you are, say this is your home. Say this is your office. Okay. Now say this distance is say 10 kilometer. Now, what is the amount of time that you are going to spend, assuming considering Bangalore traffic, 1 hour? Okay. Now, the same you are, are probably you have got a better roads or a different thing. So now this distance 10 kilometer, you are reducing it to say kind of say 6 kilometer. Okay. Now what will happen to your overall travel time? So this 1 hour can get reduced say to 40 minutes. Correct. So this 1 hour in case of 10 kilometer and 40 minutes in case of 6 kilometer. Now what is that you are trying to do here? What is that? What do you understand from this? Now you reduce the distance. Basically, the length reduces, and your delay, the amount of time it takes for the charging, gets reduced because the charges has to travel less distance only. Okay, so that is what we always consider like kind of say L. When L reduces, your delay usually reduces the charging time. Basically, the say for example now say this is the input. Now how much time does it take to charge, the change the output state? Now in case of the 90 nanometer, okay, it is going to be say kind of 40 ps. Okay, and in case of 65 nanometer, you would still have say somewhere around 35 ps, and also your device size would have been lesser. So this is your size of the device. So whereas in 65 nanometer, it is going to be say something like this. So you are getting two benefits. One is you are getting less speed, and also kind of reduction in the area. Okay. So sorry, are there any questions? Yes. Maybe we will talk more on that actually, Bala. Okay. See, I do have to cover on the say for example the whole things, and then there are different capacitances associated with this MOSFETs and everything. Okay. So I'll have to cover, but let's quickly, we are just touching, we are trying to learn the ABC of MOSFETs. Okay. Let's quickly, I wanted to finish at least this slide for today, so that like people can go and revise whoever is new to this MOSFET. Okay. Now, so length, if the length is reduced, then your delay, there are chances, your delay also gets reduced. Now, let's say your next thing is your width, the transistor width. Okay. Now remember, any transistor that we draw like this, okay, it is always we write it like W by L, something like this. For each and every transistor, we will have a W by L ratio. Okay. Now, if the width increases, now for the same length is consistent, when a length is constant. Now, if the width is increasing, what is the meaning of your delay? What happens to your delay? So when width increases, so assuming length constant, see delay decreases because there are a lot of area. See, the charges can travel on in parallel, and they can kind of charge this drain quickly. So when the width increases, your delay decreases, and assuming your length is kind of constant. Okay. Now remember this. So both W and L, they affect your overall performance of the transistor. They both affect your performance. That means what? If your L is kind of high, obviously your transistor is going to be kind of having little on the higher side delay. The delay would be on the higher side. Now, let's say if your W is kind of high for a given technology, we will have a lesser delay. Now, this is the place where you need to understand. Now, just W I said, higher the delay, we will, when higher the width, we will have a lesser delay. Now remember one thing, in industry we will just have, say, buffers and inverters and everything. Okay, now we will have inverters with multiple w's. So that means what? So there is something called drive strength. Just write down what is the meaning of drive strength. Okay, so you will have, see, INV inverter underscore x0. Okay, now there would be something called x1. Now there would be something called x2. Now there would be something called x4. Okay, now what is this meaning? This meaning is, this meaning is you have a bigger width. So if you are going to drive a smaller load, you can use this x0, which is kind of, lesser width. Say it's simple, right? Say for example you have a bigger tank. Say this is a kind of, the water tank. Okay, now you have a small tap for small buckets, and you have a bigger tap. Let's say you wanted to fill the tanker. Okay, now, so you won't be obviously using the small tap for filling tanker because the time would be high, right? So the same way, if you have to drive a bigger load, okay, so you need W higher. The W should be higher. So that means what? Uh, Less load. Okay, you can use lower width, lower width, and if you have a bigger load, okay, lower width, less load, you can use, lower width or less width. Now say you have a bigger load, then you definitely need more width, more W. Okay, remember, so this is just a concept. Now you understand it, like we will learn how to design a circuit with different drive stands and all of that. Okay, so any question on this MOSFETs, basically the WL, and how, what are the different types of MOS and etc. Go and spend some time, try to understand, because this is what you are going to work, probably, or probably you would be making as a, as a career for you, right? Because let me tell you, I did not learn any of this in my college. Okay, when I was, in my college, so I did not learn, any kind of CMOS, or, I did not, basically there was no VLSI, on my thing. It was kind of elective, which I didn't know that, I have to, take this VLSI, to get in. But I took something called digital system design with FPGA and etc. So these are all things that I learned later, because I need to definitely know how a MOSFET operates, and, because I was working on CMOS technology. Okay. Okay. All right. So I hope you guys have got an idea of what is the meaning of W and L and how they are affecting the delays and etc. Because these are all some things would be asked in your interview for sure. Okay, even sometimes would be asked in your written test also. Okay. Okay, now moving on, I may not be able to continue the class completely now, because this kind of, bigger topic. So the modes of operations, we will just, quickly glance it so that you guys can go and refresh it. But what we will do is we will learn this whole topic in depth sometime next week. Okay. So today we'll just quickly go over what are the different modes of operations and what is what. We will not get into more of details, but just a quick glance. So MOSFET operations. So there are basically three types of modes. So basically one is cutoff, and The next one is kind of the linear, and then there is something called saturation. Now when I say cutoff, basically the transistor is said to be in off condition, so the transistor is not operating. Okay. Now when you say linear, the transistor is said to be in operating condition, but the charging is happening. The charging is actually happening. Now saturation, when I say saturation, it is still in on mode. Okay, charging is already done. That's the basic thing. So it's basically three conditions. So saturation, cutoff, and linear. Now remember one thing: cut if you are working on a digital ICs, digital circuits. Okay. Now you would be really, you would be have to bother only two states. One is cutoff, and another one is saturation. Nothing else. Linear is something that we don't even bother. Okay, either we operate at 0 or 1, and also we always operate at strong 0 and a strong 1. So remember this, just write down what is the meaning of strong 0, strong 1, okay, and weak 0 and weak 1. So you can just go and read this and come to the next class. We'll explain in depth, you will understand. Now, so coming back to the same three modes of operation. So digital guys, so ideally speaking, we use, probably we operate it either in cutoff mode or kind of saturation mode. We don't prefer staying in linear mode for long and all. So now who uses this linear mode? So linear mode is basically the analog guys. So the analog guys use this linear mode. Okay, so all their circuits that they design would be kind of operated in kind of linear mode, and they look at gains and many other things which I have zero knowledge. I hate analog, the portion, because I cannot, I don't have that, skill to be an analog thing. So I chose to digital, physical design area, and I'm here today. So analog, it is totally a different ball game. You need to understand a lot of equations and etc. So that's the reason I'm here. So analog guys would use this linear, and the digital guys just uses only the cutoff and saturation. Okay, so there are some things that be important things. What is a condition for your each mode? Okay, so cutoff, what is a condition? And linear, what is a condition? And saturation, what is a condition? So try to go through it. Next week we'll explain in detail. And the drain current. So during the cutoff mode, the drain current would be zero, and in linear, the drain current would be derived based on certain formula. In case of saturation, it is a different formula. Okay. Uh, so for your information, I am not interested in you mugging up any of these equations. Okay, you don't need to worry about any of the equations or any of all these things. Just that I want you to understand the concepts very well. That's the only thing. I don't get into any kind of equations. Mainly this kind of solving equations and etc. More of concept is what I would like you to learn. That is what would be covered in the, or probably will help you in interviews, or when it comes to your problem solving in the industry. Okay. Okay, so I'll just walk you through what are the slides that I have. Okay, so that you get an idea. So MOSFET operations, three modes of operations. Okay, and second order effects. Okay, these are all your second order effects. And then we will also talk about power dissipations, and what is the meaning of static power and what is the meaning of dynamic power. Okay, and you have CMOS inverters, basically the schematic and then layout and etc. Circuits, how do you design the circuit and etc. And use this basic information to design a circuit like this. Okay, and all these things we will learn in the upcoming classes. My only request is I just want you to spend time, revise your fundamentals, and come to the class. It would be easy for you to grasp the information that I'm actually sharing. Okay, I think we'll stop here because if I pick any kind of topic, it would go for at least minimum half an hour to 45 minutes, and let's not do that now. We'll continue next week. Okay, that's all for today, and I will be here for some time. If you have any questions, you can ask. Let me just exit this tool. No questions? See, another week or two, we will finish this basics of this MOS, because these are all things that you really need to know. Okay, and then because you need to know what are the different layers, what is this meaning. So without me covering all this, it would be tough for people to understand. Okay, so because PD is nothing but you knowing what is the meaning of physical library and what is the meaning of timing library and etc. Okay, so the actual PD thing would be coming into picture. It would take at least minimum a month, please. I mean, minimum a month plus. The reason is uh, there are a lot of things that you need to learn about something called libraries and inputs and something called the SDC. So they are all kind of PD only. So ideally, we would be finishing this whole basics of this MOS probably in next two class, because next class we have to cover all these basics of MOS, three modes of operation and second order effects, power, and then we will try to go through the CMOS circuit design. And the last class would be another last class of this basic would be completely you developing the layout like this for a given cells. So that the reason why I am trying to you are not going to be developing layout, but you need to know, you have to work with such layouts, so you should know the basics of layout so that you can do a better job in the PD. Okay, so ideally the next two classes going to be uh, completing the whole CMOS. Okay, and then after that we would be kind of so December 25th is falling on Sunday, we would be moving your classes to Saturday Sunday both the days. um, so we have to work it out, and yeah.